You ever wonder what's actually happening inside an AI's brain when it learns? It's not some abstract magic. It's really just a search. It's an epic quest to find the lowest point in this huge, invisible landscape. So come on, let's grab our hiking gear and go explore it together. All right, so let's get right to it. How does this whole thing really work? Forget all the crazy sci-fi stuff for a second. At its very core, machine learning is just about getting better by making fewer mistakes. But how does a machine even know which way to go to get better? To really get this, we need a good analogy. So, I want you to picture this. A lone hiker, totally lost in a deep, foggy valley. Their goal is super simple. Find the absolute lowest point. That hiker, that's our learning algorithm. And their journey? Well, that's the secret to understanding how machines really learn. Now, this whole journey has a technical name. It's called optimization. Every single step our hiker takes is like a tiny tweak to the AI's internal settings, what we call its weights. The whole point of optimization is to find that one perfect combination of settings that leads to the smallest possible error. That's the sweet spot. This right here is what our hiker sees. This massive, rolling landscape is what we call the loss surface. Every single spot on this surface represents a different configuration for the network, and the height of that spot tells you how much error or loss you're getting. So our hiker's mission is pretty clear, right? Get to the very bottom of that valley where the error is zero or as close to it as possible. Okay, so our hiker's ready to take their first step. But their first strategy, while it kind of makes sense, has one huge problem. It's ridiculously slow. We're talking like trying to walk across a country by taking just one step a day. This first, basic method is called batch gradient descent. In our analogy, this would be like the hiker stopping, pulling out a bunch of surveying equipment, measuring the slope of the entire valley, averaging it all out, and then taking one single step. You can imagine, if the valley is huge, or in AI terms, if the dataset is massive, this is just completely impractical. So, we needed a faster way. Enter stochastic gradient descent, or SGD. Now, instead of looking at the whole valley, our hiker just looks at the little patch of ground right at their feet to decide where to go next. And the path they take looks like this. We've traded being careful for being fast. And yeah, we're moving, but it's this noisy, inefficient, zigzagging path. The hiker's kind of lurching all over the place. They're making progress, sure, but it's a really bumpy ride to the bottom. Clearly, this hiker needs some better gear. The solution wasn't just about moving faster, it was about moving smarter. And this realization kicked off the development of a whole new set of tools, what we call optimization algorithms. The first big upgrade is something called momentum. Think of it like this. Instead of just walking, our hiker is now rolling a heavy boulder down the hill. That boulder doesn't get thrown off course by every little bump or dip. It builds up momentum, smoothing out that wild zigzagging and just plowing ahead in the right general direction. Researcher Sebastian Reuter put it perfectly. You push a ball down a hill, it gets faster and faster, and its own momentum helps it power through the little obstacles. That's exactly what this technique does. It helps dampen those crazy oscillations and seriously speeds up the whole journey down. But the next evolution, that was even smarter. This is where we give our hiker a serious tech upgrade, adaptive tools. Think of it like a pair of high-tech hiking boots. Algorithms you might have heard of, like ADAM or RMSprop. They automatically change the hiker's step size. They take these big, confident strides when the ground is flat and easy, but then they switch to small, careful, precise steps when the terrain gets steep and dangerous. And wow, the difference is just incredible. You can see the old way, this wandering, zigzagging path that takes forever. But then you see the path carved by the adaptive optimizers, the ones with the smart boots. It's so much more direct, so much more efficient. It just gets to the bottom with way less fuss. Okay, so our hiker is totally geared up now. They've got smart boots, they're using momentum, they're moving fast. But all of this relies on one huge, unspoken assumption. We've been assuming that the hiker actually knows which way is downhill to begin with. We've kind of skipped the most important part of the puzzle, right? In this thick, soupy fog, how does the hiker even know the slope of the ground right under their feet? For an AI with millions or even billions of settings, how do we know how to tweak each one to make the final error just a little bit smaller? The answer, well, it's an algorithm that honestly feels like a magic trick. It's called backpropagation. And to stick with our analogy, I want you to imagine that every time the AI makes a mistake, an echo of that mistake travels backwards through the entire network.
This echo carries a tiny message for every single connection, telling it exactly how much it messed up and contributed to the final error. It's the ultimate feedback loop.
So here's how this echo works. First, you figure out how wrong the network was at the very end. That's your error. Then that error signal starts its journey backward, layer by layer. As it passes through each layer, it calculates how much that specific part was to blame. And finally, it uses that blame score to tell every single connection exactly how to change to do a better job next time. It is an incredibly clever way to make millions of tiny adjustments all at once. So this whole process, finding the bottom of the valley using this magical echo, this is the engine that drives almost all of modern AI. But this hiker's journey, as smart as it is, isn't perfect. It comes with its own set of pretty big problems. As powerful as all this is, it creates some fundamental limits. These are the really big, open questions that AI researchers are trying to crack right now to build the next generation of intelligent machines. First up, there's the forgetting problem. If you teach a network something new, it can actually just overwrite and forget what it learned before. Then there's what's called the locking problem. A great way to think about it is like a bucket brigade. The person at the front of the line can't adjust what they're doing until the very last person has gotten the bucket and sent a message all the way back. The whole network is locked in this forward then backward stance, and that can be a massive bottleneck. So, let's just pull this all together. What's the one big idea you should walk away with? It's that we've powered this whole AI revolution by doing something beautifully simple. We took the abstract, fuzzy problem of learning and turned it into a concrete, physical problem, finding the lowest point in a really, really big valley. And to find our way through that valley, we've given our hikers some seriously clever gear, tools like Momentum and Atom to move fast and smart, and most importantly, we gave them a compass, that magical echo called backpropagation, which guarantees that even in the thickest fog, they always know which way is down. But that leaves us with one last really interesting question to chew on. This entire way of thinking is built on one idea: always go downhill. But what if the most creative, the most intelligent, or the most human-like answers aren't at the bottom of the valley? What happens when the best solution requires going uphill for a while? Well, that's the next great quest.